Hi folks, and welcome back to Physics with Captain Rod. Making this video here to discuss with you energy units for thermodynamics. So energy can be written in lots of different units, right? Here's some common ones for thermodynamic problems, right? One is called the kilowatt hour. And first of all, let me explain, this thing might sound a little weird. Why is this thing a unit of energy? Well, remember that power is change in energy over change in time, or work divided by time, either one. And if I take this equation and basically do this, right, put the delta T on the other side, change in energy is power times delta T. So anything that is a power times a time is a unit of energy. So I can make one up off the top of my head. Horsepower is a unit of power. So if I took, say, 3 horsepower and multiplied it by 5 minutes, I would get 15 horsepower minutes. This is a unit of energy. Right? Kilowatt hour is very similar to that. Right? A kilowatt hour, all right, I've defined it right here. It's the unit of energy measured as 1 kilowatt of power extended for 1 hour. So basically what a kilowatt hour is, 1 kilowatt hour, right, is 1,000 watts times an hour, which is 3,600 seconds, which is 3.6 times 10 to the 6th joules. So a kilowatt hour is equivalent to 3.6 times 10 to the 6th joules. Now the reason the kilowatt hour is used mainly for your electrical bills is it just makes it really simple to do electrical calculations. A quick example, if we had, say, a 1,500 watt oven, right, the power of that oven is 1.5 kilowatts. If we ran that oven for 2 hours, then the energy that we would use would be 1.5 kilowatt times 2 hours, which is 3 kilowatt hours. Now, my current electrical bills, I'm getting charged right around 20 cents per kilowatt hour. So in this example here, my oven example, I would get charged about 60 cents. 60 cents to run that oven. Right, other units of energy that we're going to be talking quite a bit about, right? The calorie is another common unit of energy in thermodynamic problems. And here's how the calorie is defined. Heat needed to raise 1 gram of water by 1 degree C. The food calorie is another common unit in thermodynamics. And a food calorie is 1,000 calories, or it's also called a kilocalorie. So when you say drink a Coca-Cola or something and it says 60 calories, those are food calories. And what that means is that's 60,000 little c's. I guess I don't need a decimal there. So the calorie itself, the heat needed to raise 1 gram of water by 1 degree centigrade, is usually represented with little c's, and a food calorie is usually represented with big c's. And again, that's 1,000 calories or a kilocalorie. Right? Another unit that we'll talk about from time to time, the BTU, or British Thermal Unit. Right? Here's how it's defined: heat needed to raise 1 pound of water by 1 degree Fahrenheit. Right? So these are all units of energy that we will talk about from time to time and may show up in your homework. The kilowatt hour, the calorie, the food calorie, and the British Thermal Unit, or the BTU. All right, and here are some conversion factors for going back and forth between them. All right, another important thermodynamic concept is efficiency. So efficiency, I've defined it here. It's your desired energy output over your energy input. So if I were to write that in an equation form, your efficiency is equal to your energy out divided by your energy in. It also works for powers, right? If you know power outputs and power inputs, you can say that your efficiency, is equal to your power output divided by your power input. Okay, so some examples. The human body is roughly 25% efficient at converting energy in the food to useful work. So what that means is basically, right, if I take this formula here, 0.25 is equal to your energy out divided by your energy in. So if I wanted my energy out to be, say, 100 joules, and I solve this for my energy input, you would get 400 joules out of that. And what that means is that you would need to break down and absorb 400 joules worth of energy to do 100 joules worth of work. Now, the other 300 joules just ends up leaving in the form of heat. So your skin stays warm and air comes along and takes some of that heat away. Another thing is that you radiate energy. The human body radiates energy at about 80 watts, about similar to a light bulb. Okay. Car engines, they're roughly 20% efficient. All right, so that's a little bit on the depressing side. So when we're paying, $3 a gallon of gas, or for a gallon of gasoline, only about 20% of that ends up getting converted to useful work. So of the $3, really only 60 cents of it is converted to making the car go down the road. The rest of it is just turned into heat. And it's exhausted to the environment or given to the environment through the exhaust or, by the radiator, taking heat and giving it to the air, basically. Okay. Here are some energy contents that you'll need on your homework, or they're just useful things to have from time to time. So let's see. This really, I guess I would call this a conversion factor here from kilowatt hour to BTU, but natural gas has an energy content of about, let's do it per cubic foot here, 1,036 BTUs per cubic foot. Let's see, gasoline per gallon is about 120,000 BTUs. Diesel fuel around 137,000 BTUs per gallon. Propane is one that's going to come up quite a bit. I put a few of these in your homework. A gallon of propane has roughly 91,452 BTUs. And burning wood, right? A cord of wood here has about, 20 million BTUs. So these are values that you'll be using on your homework from time to time. And they're just nice things to have around. Okay, I think what I'm going to do here is stop this video now and make a second one for the examples. So I hope you're enjoying this. Have a great day.